Hi, I'm Eileen, and I'm working with the PS team at G12 with Youyang and Isabel. Now let's ask Youyang about this project.
Hello, I am Youyang. This video is to inform you about Team G12's phone charger design that would save your battery with nothing but a laptop.
And I'm Isabel. Here I have our solar-powered boost converter, which allows us to harness the power of the sun. The system is made up of a comparator, oscillator, and boost converter, all of which are designed in order to maximise efficiency and allow us to charge a phone. We've used some top-of-the-line cooling technology to maximise our solar panel temperature and orientation, as you can see here. And can you believe it's 100% recycled?
This system can be fully controlled through a laptop API. We are able to input data from our circuit in order to analyse it in real time. We are then able to meet power requirements by simply typing in a number, or if we need to, through a manual override. All data is also saved locally to ensure it can be analysed at a later date if necessary.
Firstly, our team identified its solar panel characterization, and we found that all three solar panels have similar parameters. The solar panel is now connected to the boost converter as the input. The system of the boost converter has been optimized to give the required output power with convenient control. The system consists of an oscillator circuit, a comparator circuit, and the boost converter. The output of each system is connected in parallel combination to the cloud, and the cloud will feed a virtual boost converter which is connected to a virtual battery. By considering the effects of temperature and environmental factors on the performance of the system, our team decided to use a structure that could lift the panel off the ground and hold it at an angle of roughly 50 degrees. This design encourages airflow across the surfaces of the panel, which results in lower panel temperature.
As we implemented our design, we encountered many issues in our circuits that cannot be predicted by the LT-Spice. But thanks to Teams, we're always able to share those issues and discuss alternative approaches to our design online. In addition to that, we use Teams to check each other's progress with their shared load. For example, for the phone charger, I focused on optimizing the PWM and selection of the inductor. So there were times when Eileen and Isabel asked me about the alternative version of the circuit after I noticed that some model physically didn't work. Well, another example of teamwork could be decision of PID output range. Given the fact that maximum power point varies with insolation, we decided the best PID range that included the maximum power point by checking each other's insolation 1 hour before the test.
When it came down to testing, our system didn't actually perform quite as well as we would have hoped. We produced an average combined output of 103 milliwatts. On the day, our insolation and temperature levels were actually a bit higher than we were expecting just because of the really good weather, but our maximum power was a little bit lower than what we'd expected. And one of the main issues we had, as you can see on this fitted IV curve, was one of the solar panels had a much higher series resistance than we were expecting, so it ended up being about 2.5 ohms. So this obviously reduced the efficiency of the solar cell and then the system as a whole. Another one of our team members experienced a drop in insulation through the middle of the test, which meant that the power output was subsequently also lower, as you can see through the trend of these graphs. However, without these issues, our system did actually perform fairly well. We were able to hit the power requirements in one team member's case, as you can see on this graph here. So we are fairly happy with our design. We just encountered a few problems on test day.